This is SPE Talks 2.
Adrián Ledroz.
Hey, welcome to the SPE podcast. I'm Trent Jacobs. Today we're talking with Adrián Ledroz. Adrián, what's your title?
I'm a VP and also the chief scientist for Wellbore placement at Gyrodata.
Okay, there's a lot to unpack here. I wanted to talk about some of the technology that your company's developing and just the realm of drilling surveying technology in general. But before we got on, you were telling me that you actually didn't start off in oil and gas. So you were a biomedical engineer?
That's correct, yes. I'm a biomedical engineer. I started working with sensors, signals, processing that to extract useful information. And then similar principles, I started working on systems and sensors for downhole surveying. Again, looking at signals, getting them better to extract information, but for wellbore placement.
Okay, great. So, another example of how you can take other areas of expertise and port them into the oil and gas industry. You actually got exposed in Calgary, you were saying. Your accent gives you away, so you're not from the U.S., you're from...
I'm from Argentina, yes. So I learned my English via Calgary. I did a master's there in electrical engineer. And then that's when I transitioned to the oil and gas and the world of wellbore surveying. Okay,
well, let's talk about that. Let's talk about wellbore surveying. This is a technology that personally I have focused a lot of my energies over the years on completions technology, sort of looking at that as like one of the big drivers of the unconventional revolution here in North America. But wellbore placement and wellbore surveying is something that I'm a little bit less exposed to through my reporting. So I was going to see if maybe we could just start off, even if it's for my own benefit, if not the listeners. What is wellbore surveying? How did it start? What's the evolution of that technology arena look like?
When the whole drilling for oil started, we were doing vertical wells. There was no surveying. You just drill a hole on the ground vertically or try to keep it vertically and hit the oil. But then we started needing to deviate the wells to get to a different formation because of different obstacles. And then we needed to know where we were drilling. And so through the use of different methods, the first one were very primitive, and then with the evolution of the transistor, the electronics, more sophisticated methods, using, first mechanical method with gyroscopes and magnetometers, and then with the accelerometers, and then spinning wheel gyroscopes, solid-state magnetometers and solid-state gyros, so you can basically deviate the well and know where you're going. And you need that information to see that you reach the reservoir and also to see the place that you thought have oil really produce at the end of the day.
One of the things we see a lot of sort of cartoons of oil wells, them kind of going into the layer cake and hitting that right target. But then you sit through enough technical sessions on this subject and you learn that like staying in the target zone is very difficult. And so some traditional technologies, one of the things, measurement while drilling, I guess, would be sort of the bedrock, if you will, of this area. It has well-documented challenges with helping people stay in the formation. So can you talk about what are those challenges? Why the evolution of this technology has continued to be needed?
Sure, yes. So the measurement while drilling usually refers to the measurement of the orientation using magnetometers and accelerometers. So they measure the air magnetic field and to determine the orientation, and with the information from the accelerometers. I'm getting a bit nerdy here, but...
that's fine. That's our audience is sort of the Petro nerd community, so feel free.
You can estimate the inclination and the orientation or the azimuth. But one of the issues is that the magnetometer will measure magnetic field regardless of the source. So you're not only measuring the earth magnetic field that determines your north, you will measure the steel on the bottom hole assembly plus any ore deposit or anything that is downhole. In addition, the magnetic field is not something static, and it has anomalies due to the crustal field and also is affected by magnetic solar storms and other things. So the reference is not very stable, and you have to model that with, well, it's possible to do it with very sophisticated models, but it's not as simple as just you run a sensor and you get your information clean.
So you have to cancel all these other influencing factors out, including solar flares and
Yes.
and the Earth's own magnetic field, which isn't static. And so I imagine that's been a difficult process to do over the years.
Yeah, and there are several companies, universities, and governmental agencies that study this, and they have magnetic models. It's also possible to monitor this in real time and apply that to the field where you are drilling. But obviously, these are cost and complexity and the procedures, and sometimes there is even a delay. So in order to continue drilling, you need to know where you are, but you need to do a correction based on what's going on. So that delays the process as well.
And traditionally, we're talking about, when I've been exposed to MWD and surveying, and this may be a little outdated, but people talk about 90-foot measurement. So every 90 feet you drill, you take a measurement, and you may realize you're pointed up, down, a little bit too far, and then you have to correct. And then that's sort of been pointed to by drilling experts as one reason for shales, highly undulated wells. Again, going back to those cartoons that we see in corporate slide decks, you see these nice straight wells, but in reality, they look like little wormholes. They're going up and down, and that kind of tortuosity is not desired, right? So people are trying to get effectively stay in zone and then get straighter wells. Is that sort of what the prize for drillers is today?
Yes, it is. That's correct. Yeah, that's sometimes it's known as wellbore quality, and yes, when you have a data point, a survey every 90 feet, and sometimes it looks straight, sometimes it looks undulated, but that's many times depends on when you stop and take the survey. If you are rotating or sliding, obviously you have an assembly that allow you to build a curve. So when you try to build a straight line, it's very difficult because it's usually a bend assembly. But yeah, until we didn't get the technology that allow us to see the wellbores with a high density of data, right now it's possible to get surveys every 1 foot if you have the right technology. So before it was just all assumptions, and people were associated this with possible problems with undulations, but they really didn't have the data to validate it. But now we can survey, the open hole, either while drilling or post-drilling with a gyro or a magnetometer, and then we can survey the casing as well and to see how straight the wellbore was. And that's usually associated with issues with the torque and drag. It may limit your how far you can take the well, because if you have all this undulation, you can imagine that the frictions become very high, and you cannot transfer the weight to the bit and continue the drilling. So there are many benefits associated with the straight trajectory.
So a straighter well, kind of like you said, with less friction, you're having fewer drilling dysfunctions, and you're able to drill faster.
Yes, and farther. And also when it comes to the time of running casing, you have less problems. If you have to install a way of artificial lift, artificial means, then again, those work much better if you are in a straight line that they are subject to bend.
Right. We've seen lots of reports. We put them in JPT about those undulations during production can cause slugging because the gas basically builds up behind a sort of a water sump. And then also if you have too steep of or severe of a dog leg, then we've seen people with rod lift, like you can rub a hole in the casing or the tubing in just days. That's a pretty well documented problem too. These are all headaches that when unconventional drilling kind of started, they weren't really discussed. But over the last, I would say last 5 years, these become pretty popular topics, and drivers trying to get people in drilling closer to the people in production, so that they can kind of see each other's own problems.
Yes, we have worked with a few companies that actually well, because of the high density data, they were using this primarily for the placement of ESPs, electrical submersible pumps. So in many cases, they have issues with the pumps like after a week, and these are very expensive piece of equipment.
ESPs are almost $1 million each.
I think they're about $250,000. But yeah,
okay.
if you break a couple, and these were lasting only for a week, and plus the lost production and the work overtime and all that. So we have shown that with the high density data, you can establish if the pumps is gonna last, or you really. There were cases in which you say, well, this well was drilled in such a way that there is no good place for it, so I'm going to have to convert it to an artificial lift. But certainly putting the drilling people with the production and completion people together has been very beneficial for this operator, because now everybody can see it's not that the drilling department drill wells and they just forget about it and go into the
right, which was sort of the accepted siloing of the business years ago. Was, drillers had one mandate, which was to drill fast, right, and bring those drilling days down from 40 to 5 or 4 in some cases we've seen in the Permian. But then as those, like I call them like the rig speed records, as those all got shattered, this topic of wellbore quality started to come up in technical discussions, and we obviously saw a lot more papers. And then companies like Gyrodata come along with some advanced technology. Before we get into some of those things, the things that you're working on and have done with Gyrodata, I just want to take a quick break, and then we'll come right back. Sign up for the JPT newsletter. This is a hassle-free way to stay connected. You can read features on technology advancements in exploration and production. You're going to get reminders on oil and gas issues, and you're going to just get general news about what's going on in the SPE and with its members. The JPT newsletter keeps you up to date with the latest technology developments. It's delivered to your inbox every week, and it's just a great way to stay ahead of the curve. We're going to include a link to this free newsletter in the show notes of the podcast. Click it, get signed up, and you're done. So, Adrian, I wanted to talk a little bit about Gyrodata, the technology you guys have been developing. You've been with Gyrodata for, you said 15 years?
15 years.
So you've seen this company really evolve, and also this space. So go ahead and tell me about, what is y'all's latest and greatest technology? What are y'all bringing to the market?
All right. Yeah, I'll give you a little background before starting. So we initially started with the gyro surveying in casing and for orientations and kickoff. Basically, that's the area they usually have magnetic interference, and you cannot use a magnetometer, so a high accuracy system was developed.
You're talking about the kickoff point, so
Yes.
you're talking about drilling the curve. Where do I want my lateral section to go out and begin? At what degree or inclination I want it to start?
Orient a whipstock.
Okay.
Yeah. If it's vertical, then you need some, the magnetometer doesn't work because you have magnetic interference, and because it's vertical, the accelerometers don't give you any idea of the orientation or tool phase. But with the gyro, you can measure the earth rotation and orient that, so you can start drilling in the desired direction. So that was successful. Then there was more interest to increase the accuracy of the wellbore placement. So we developed gyros that, with a higher inclination capability, and then a drop gyro that the main advantage was it doesn't take any rig time. You drop the tool after you get to a section TD, and when you pull out of the hole, it produces a survey.
Is that like wireline deployed, or?
No, that's just a drop. It's a memory tool.
Okay.
The wireline is good because you have you can have a lot of data density, and you can see in real time what's going on, but you are preventing the rig from drilling. And that costs money, and nobody likes to just stop the drill for surveying. So those are still used, but are not as popular as a drop gyro. Then in the early 2000s, we came out with the gyro while drilling tool, which basically is similar to standard NWD, but we take a gyro survey while drilling. So every time the drilling process stops, to make a new connection, you connect another piece of pipe then we are stationary, and that's where we take a survey.
Now you have to be stationary and no vibrations. That'll set off the measurements in the wrong direction. Is that why you need everything to stop?
Yes. Basically, the gyro measures rotation, which is a special kind of movement, I guess. Mm-hmm. And so if you have that, as the magnetometer cannot distinguish between the different magnetic fields, the gyro cannot distinguish between the different movements. So it measures the air rotation, but if you are rotating the BHA or moving it, it will affect the quality of the measurement. But then, we started with the gyro while drilling. First was limited to 20 degrees of inclination. As you go higher inclination, it become, the effect of the errors on the azimuth measurements start increasing. So through a series of development, we first came up with the GWD 40 and then 70. And in 2012, we came up with the GWD 90, basically a tool that can survey in any orientation while drilling.
So if I have a really steep inclination on my lateral, that used to be sort of a challenge for you to get an accurate measurement, but now I can come down off my kickoff point and go up at a pretty high angle,
or any angle,
you can still be accurate.
But that was based on the spinning mass gyroscope, which is basically like a tabletop principle. It has a small motor that make a mass spin, and due to the physical properties, when this is subject to rotation, it changes the signal output, and we can use that to determine the azimuth. So in 2012, we started developing, we started looking at what is called a solid state, similar to what is sometimes called MEMS technology. Basically, no moving parts. It's a different principle of operations, but it still is a sensor that measures rotation. So we launched, our first product was in 2018, a memory tool similar to the drop I described, but instead of the spinning mass gyro, it's a solid state gyro. And then we launched last year the GWD version of that, the gyro while drilling using this technology.
Okay, I have a few questions. First let's back up and just talk about gyros. So and accelerometers and all this whole world. Has why is that technology sort of just entering the scene in the 2000s? I look at like my smartphone, and we assume that the iPhone's made a lot of like sensor technology cheaper, and we always hear about gyros in this context. And I'm wondering, was that a driver, or was gyros that area of technology? It was just it's time to be commoditized or brought down and advanced and put in something that can drill a well?
Yeah, the first gyros that we started using in the 80s, those were from the aerospace industry. At the time, there was no GPS, and there was a lot of driver for getting gyros to be more accurate. So you can navigate with a plane or a satellite or a missile using these gyros and accelerometers. Then with the advancement on the GPS and then becoming more popular, the driver for having high accuracy gyros kind of went down. But as technology advanced and all that, there was some driver to get gyros on your phone. But those were kind of a low accuracy, and more importantly, probably is a limitation on temperatures. Those sensors don't operate higher than 60 degrees centigrade would be the highest in a desert. But downhole, that won't get you very far. But there was a development as well of more safety features in cars and some military applications that needed the high temperature. So that also drove the manufacturers to look at sensors with more accuracy, but also with more higher temperature capability. That's where we found these solid state gyros that we are using because for a car, usually they are rated to 125 degrees centigrade, and for some military application as well. So became again, there was an incentive for this company to develop this technology. And now if you add the fact that for many applications, you don't want to be connected with the GPS, you want to be off the grid. So if you have a good gyro, good accelerometer, you can navigate without depending on the GPS and without anyone knowing. So there is also more developments on that area.
And so, you used to have, actual spinning mass gyros, right?
Yes.
That was sort of the entry for Gyrodata. But what's special about solid state? I think you mentioned that it can handle better, higher temperatures. So that sort of takes you into the HPHT world of oil and gas drilling.
Yeah, the other aspect was the spinning mass gyro, because of the nature. If you subject it to a lot of shock and vibration, you start generating some small imperfections or bending inside the gyros that created what is usually known as a mass imbalance. Imagine it's a spinning wheel, and if you keep shaking it, something will happen to it, and that created errors in the measurements. This solid state, because it's a different principle, doesn't have this error, which was one of the main contributors to the uncertainties. So now it's a gyro that basically can take as much as a magnetometer regarding shock and vibration. So
now, at the risk of getting into the weeds here, so are there any moving parts in a solid state gyro?
Well, there is a small vibration, but it's in the order of the nanometers. So there's a vibration that when it's subject to rotation, it changes its nature, and you can sense that, but it's really not something that you would be able to see. So for all practical purposes, it doesn't have any moving parts.
And so it sounds like a pretty big leap from having, the spinning mass gyros. And so I'm just curious, how, in your eyes, how big of an advancement in technology is it? And, how many years did that take to develop? And there are other companies in different verticals using solid state gyros for other things.
Yeah, there are a few other companies. For us, it was we wanted to maintain the accuracy of the spinning mass gyro, which is very accurate. The problem was that the calibration or the sensor could change on the drilling environment. So for us, we started this process in 2012 until we came out with the first product in 2018.
But so that's 6 years of R&D for you guys.
Yes. To give you an idea, we went from a tool with all the electronics required to run the gyro from 16 feet to 3 feet. So that's a great advantage for downhole. We reduced the power to about 15% of the previous technology. So this makes the battery last long. We now can drill the whole well, survey while drilling, and survey while pulling out of the hole. So there are many advantages.
Are you using mud pulse telemetry to send the data back up?
We can use any technology. Yeah. But also the number of electronics board requires to run this gyro went from 8 to 2. So the reliability increases a lot. You have less components, less connector, less wires. So
and the subunit's just 3 feet long.
Yes.
I love when things get really small, but they help make giant decisions. And one thing that you guys and other people have talked about over the years, especially with regards to staying in the target location or horizon in shale, is the ellipses of error. And so have you seen, so for all those, for the listening public here, we're sort of talking about this, it's an ellipsis, so it's like an oval shaped sort of dotted line that goes around the center of your drill bit. And this is the error area that you could be either dead center, or you could be 15 feet up or 15 feet down. And but we can tell you if you're in that circle. It's sort of like the cone of uncertainty for hurricanes, right? We can tell you you're in here or out of here, but not precisely where you are inside of that ellipsis. And so have you seen this ellipsis of error shrink because of the technologies like this?
Yes. of course, it depends on the wellbore profile and the location and the actual situation. So for a vertical well, it doesn't make a lot of difference. And most of the error there comes from the misalignment, how well you are centered on the tool.
And we know that no vertical well is truly vertical, right? So
Right.
even in a vertical well, you're never really drilling straight down. You have an ellipsis of error even in that scenario.
Correct, yes. But it doesn't make much difference whether you use one sensor or another to measure the orientation, because it's mostly vertical, and the error sources is mostly the misalignment and the inclination. But when you go to your deviated well, especially the unconventional with the long lateral section, then you start seeing a big difference. And we see reduction of, depending on what tool, and again, the orientation, if you are north or south, is not the same as east or west, but we see reduction of 30 or 40% on the ellipse of uncertainty, which is, we feel that is really important. Sometimes there are unknowns, and people drill these wells and they don't know why. Well, here I got good production, and this other well, following the same principles in the same formation with the same driller, I got half of the production. But if you don't have a good measurement of where you are, you may be really close to the other well, and you are taking oil from the other well.
Right. I mean, you bring up a great point, which is there's even within trying to get spacing measurements down, we've seen the analyst groups try to do this from public data, and it's actually very hard to know where the laterals are. So when we look at well spacing, people are like, well, they're 300 feet apart, and then the sort of the purists will say, well, 300 feet at which point along that 2 mile lateral? And even those are hard questions for everybody to answer, just because the surveying is so tough.
And I was on a webinar, actually, they were doing that. They were analyzing public data, and I asked, well, how do you know that the wells were placed where they say they were? And say, well, I'm looking at the data, and it says that this is the position, so this is the position. But they don't take into account this uncertainty, and the larger the uncertainty, the more that this analysis becomes kind of useless, because you may be analyzing this, but the wells can be very close or far apart, or even outside the formation, or even sometimes crossing some lease line, and you are drilling on your neighbors.
To your point, maybe you can comment on this too. Over the years, we've also seen, the geomechanics crowd within shale, which is a relatively small group, but they carry a big stick. And when they talk, I always listen, because they're becoming sage these days, as more and more companies learn that if I place my wellbore just inches in a different position, then that could direct the outcome of this well. And so they're talking about these getting within these minute facies of the horizons, so that they can take advantage of all the geomechanical benefits and the stress and all this. But if they're off by, and some people say inches, if we're off by inches, then we will have a poor completion in this segment of the well. So that, there's another crowd that says, well, we can never be that accurate, and should we even try, because of how much work it would require to be that accurate. But you must see the whole spectrum of people who want to get to that nth degree of that one, bedding plane, versus people who are like, just stay within this 100-foot, source rock, and we're good.
Yeah. I think there is a bit of a misunderstanding or misinformation on the different departments of the companies, with the geologists and the drilling and the completion. The targets, sometimes they have not everybody understands the uncertainty related. When they do the reservoir model, there is an uncertainty associated with that. Mm-hmm. And that transmit that information into a target, and then transmit that to the directional driller, how precise you need to be. There is, when we say, well, this is the uncertainty that this survey tool will produce, a lot of people are really surprised to see, well, I thought because you give me a line that the well was on that line. It's, well, that's what the survey says. You are likely to be there, but you are as likely to be at any other place in the ellipse of uncertainty.
So we draw a picture of the reservoir, then we say, I want to stay within this layer. And then, so that's one picture. Then we superimpose another picture, which is the Wellbore survey. And so, we're looking at two things that are basically estimates. And you're just trying to reconcile both of them and stay as accurate. But I think you're sort of speaking to the unknown aspects of drilling these wells, is that there's always some inherent inaccuracy. You're just trying to get closer and closer to the bullseye incrementally, but where that bullseye is, it kind of depends on the eye of the beholder.
Yeah, and imagine if you drill this well and your line is on the actual reservoir and you don't get any oil, what they do is then they shift the depth or the placement of the reservoirs, instead of saying, well, maybe the survey is wrong and we didn't hit the reservoir. So you have to close the loop, and it may result in important decisions from abandoning a field or making different assessments.
Now, we had a story on JPT on our website not long ago about sort of the diverse market in Texas. I believe there was almost 80 MWD and directional drilling companies serving just the Texas market, which, if you're not familiar, represents about half of onshore U.S. production, almost like 4.5 million barrels a day or more. And so it's no surprise, but I was really surprised by the diversity. Not that there was so many people coming in, but just that there was all these companies, and they were actually, nobody really had more than 10% market share. So, when you look back on your 15 years in this business, do you have thoughts about watching the uptake of this technology? Was there a point in time where operators, especially in the U.S., they're always looking for the lowest cost well, where they weren't using these technologies, and then they gradually gravitated towards them? No pun intended there.
Well, I think as you have so many MWD, you mentioned companies, service companies, it's the same with the operators. So you have operators just drilling one well, and operators, drilling a large number of wells. I think also because of this, all these different operators, many have different goals. Some wants to drill a well and stick to the field and really produce as much as they can. There were a group of people that actually were drilling wells and selling them. So,
yeah, the flippers.
Yes, and then their cases, they're just looking at, drill as fast as you can and then move and drill to the other one and try to sell it as fast as you can and so on. So what we see is usually the bigger companies that try to develop the field, and they're going to stick to their wells. They try to do a much better job of placing the wells in the right place, build them straight so they can put artificial lift means and don't have to spend a lot of time and money on workovers. So it really depends. Some companies provide quality control and a very good job, but sometimes, the small operator or they don't have all the infrastructure, and they don't look at the future that far. They just
right. We've definitely seen how business models dictate, your development strategy and how you frack these wells and where you land them. One of the other things I wanted to get you to talk about before we jump off here was, some of the HSE type issues, the collision events that you can try to prevent by doing, robust MWD and gyro surveying. I've actually been on location where they drilled a new well within 5 feet of the heel of a parent well, and when they tried to frack that toe stage, they went right into the next stage. So this would be frack bashing, frack hit, and they weren't using the highest, the latest and greatest technology on this. So they only realized towards the end of the project that they had landed that well so close to another one, and they paid for it. They actually said if we were trying to hit that other well, we couldn't have done it, but we did. And so, can you talk about those kind of events that your technology can help prevent, and how it all folds into well spacing?
Yeah. So usually there are two types of collisions, and usually they're classified either as HSE, in which you have really an important damage to the environment, health and safety. There can be some casualties. So that's obviously something that nobody wants and nobody plans for that. And then you have the other type of collisions that can just have a financial impact. So the one that you described probably was more a financial impact, and some companies even plan or take into account, well, if we have a collision according to the well plan and the ellipses of uncertainty, if the ellipses of uncertainty start overlapping, then that means that you may have one well very close or actually hitting the other well. But they look at the consequences, the pressure if one is producing or if it's an old well, and they may live with that because, it's just
they got to model it out and say how often is that likely to happen, how much will it cost?
Yes, and how much is going to cost me to deviate this well or survey or stop and survey properly and or range or use some technologies to stay away. Usually if you are offshore or if it's an important project and you have a live well producing with pressure, you wouldn't make that because the cost of doing a successful relief well, your reputation, the environmental damage, the casualty, you cannot afford to do that. And so people then will take the measurements to
on a $40 million well, it's a no-brainer, right? It's the $6 million well, the $7 million well where you gotta you gotta make these decisions.
Yes, and I think there is a lot of there are a lot of collisions happening, but because it's just a financial impact and it happens downhole, there is no result. Nobody see oil flowing. They are just live there and you just drill the next well and cross your finger and hope for the best.
But with good surveying technology, there's really no reason to have to worry about a collision.
Yeah, you certainly can avoid that if you have the proper procedures and technologies and it's something that is on your plan to avoid drilling the other wells. Yes.
Well, I think we're out of time. I really appreciate you coming on the show, Adrian, and talking to us. Was there a last thought that you had on this technology arena? Is there something on the horizon that you're looking forward to, sort of the next evolution of this technology area?
Well, I think it would be the more integration, having more sensors on the BHA. I think having the magnetometers, the gyros, and the accelerometers probably all the time is the best solution. So you can get the best of the two worlds. And I look forward to that. We are working on that and also integrating this into rotary steerables. So right now those are based on magnetometers, but I think it would be an advantage to have the solid-state gyro technologies in there so you can automate the drilling aspect. So
a lot of this you think is definitely a stepping stone, sort of a prerequisite for the holy grail here of this sector, which is automated drilling. Yes. I think that's it's a key part of it, and it's gonna continue evolving, and I think gonna result in tools incorporating these technologies. Adrian, where can people find you to learn more? Are you on LinkedIn? You on Twitter? Where do you live on the interwebs? I'm on LinkedIn. I'm on there, so just you can look for my name and contact me. I'll be happy to answer any question or follow up with any conversation. I'm also part of the steering committee on Wellbore survey accuracy. So I'm the program chair there. So if you go to that IACWSA.net, you can contact me there as well. Okay, we're going to put links to that on the show notes. All right, we want to keep the conversation going, so please use the hashtag SPE podcast wherever you find us on your social media. Reach out, send in your comments, and leave us some reviews on your podcast platform. We want to hear from you. And of course, we want you to read JPT online and in print, so make sure to bookmark us and keep checking in for new content. I'm Trent. See you next time. SPE Podcast is powered by the Society of Petroleum Engineers, whose vision is to advance the oil and gas community's ability to meet the world's energy demands in a safe, environmentally responsible, and sustainable manner. Learn more at SPE.org.